Okay, so now I'm gonna go over section 11.5, which is base E, exponential functions and log functions. So basically, if you do 1 plus 1 over n to the power n, that equals E as long as n is extremely large. You can check that on your calculator. But what is E? Your calculator has an E key. If you do second division sign and hit enter, it's an irrational number, 2.718281828. It's never ending decimal. Or you could go to second ln right there. It gives you e to a power, so you want to do e to the 1, and then you can get that number. So e is roughly 2.718 blah blah blah. It's an irrational number. And if you do 1 plus 1, say over 10 millions to the power 10 millions, you get that number. You keep increasing n, that expression is going to equal 2.718. That's something you could do on your calculator. Uh, so E, just keep it in mind that it's roughly 2.7, so we can use that estimation. So if we want to graph, say, e to the x, to graph y equals e to the x, we know it's exponential function. The base is e, which is greater than 1, so it's going to look like the exponential growth, if you remember what we did with basic exponential functions. And you can confirm that by making a t-table, plugging in those values. You have a calculator, so you do e to the negative 2, which is roughly 0.14, e to the negative 1, 0.4, e to the 0, e to the 1 is 2.7 roughly, and e squared is 7.4. If you plot them, you're going to get that shape. And based on this, if you want to graph like e to the x minus 2, that means the basic graph is e to the x, and then you go down 2. So I'm going to move 0, 1 down 2, and I'm going to move the x-axis down 2, and then copy and paste. So this would be y equal e to the x minus 2. And then say I want to graph e to the x minus 5, where the minus 5 is with the x. So this is shifted right 5 units. So e to the x, which I'm going to copy, so we know how we're going to shift it 5 units. This would be e to the x. It goes through 0, 1. So if you shift this 5 units to the right, so you're at 5, 1. So the whole graph has to shift 5 units to the right. This is 5 units. This is e to the x minus 5. And say you have another example to graph y equals negative e to the x plus 1. So the negative in front of the function, it means you flip it in the x-axis. And then the plus 1 means up 1. So if you take e to the x and flip it in the x-axis, it will be, this is negative e to the x. This is 0, negative 1. But that's not our final destination, because we have to move it up 1. So you move this up 1, you move the x-axis up 1, becomes y equals 1, and that would be your final graph. Y equals negative e to the x plus 1. Now, if you want to graph, say, y equals ln of x. Well, we're going to talk about, we're going to talk about this in a second. We're going to talk about this in a second. So remember we talked about common log. In the common log, the base is 10. There's natural log or Napierian log. The base is e. And for base e, instead of writing log base e of x, we write ln for Napierian or natural log of x. When you see ln, the base is automatically an e. And you can see that log right there, ln. And you can see it's base e because there's e in the background, so you know it's the base. So if you want to do, say, ln of 1, that's log 1 base e, which is 0. Log 1 to any base is 0. Okay? Okay. So now an application on E, if interest is compounded n times per year, we use this formula. Remember we went over this. Okay? That's compound interest formula if interest is compounded n times per year. If interest is continuously compounding, in this case, the number of times it's compounded is huge, so it's infinity. We don't say equal, it just goes to infinity. And we know if we look at that formula, we can't use that formula anymore because n is infinity. So what we're going to do, we're going to look, remember how we defined e? We said this is e if n is infinite, and we know now n is infinite. And if we want r here, then we have to put r there. If we want t, we put t in the exponent times by p. So we use PERT. When what? Interest is continuously compounding. That's the formula we use right there. So for continuously compounding, we use PERT, principal. R is the rate, t the time, and a is the amount. If it's any other compoundings, then we use the first formula. So for any compoundings, for continuous compounding. Any compounding, continuous compounding. So for example, if you look at 36, page 958, if you look at 36, page 958, what they want in there, it says use the formula A equals PERT. So they're telling us which formula to use. Given the following values of P, so P is 20 grams, we'll put that in there. R is 6.5%, so 0.065, and then T is 100. So we put that in our calculators to get the answer. So it's 20,000 second ln. Okay, second ln, and will give us E with the power, second ln. And then in the power, we're going to do 0.065 times 100. So interest is compounded continuously, and that's the amount you have if it's 20,000. But I think it's 25,000. I did it for 20,000, which is okay. That's what I get if I do 20,000. 13302.832.66. So 13 millions So we're going to call this 36 star because in 36 this is 25,000. Okay, it doesn't matter. All right. So we know that log base e of x is ln of x. And we also know that if the bases are the same, we get x. If it was b log base b of x, it's also x if x is positive. So if you use e for the base, like log base e of e to the x, it's x, which means ln of e to the x is x, because ln is log base e. And if we do e log base e of x, it's x, which is the same thing as e ln of x is x, as long as x is positive. Remember, logs don't behave well with negatives or 0. So what is ln of e to the 4? Again, these cancel each other out and you get 4. Number 48. What's ln of the fifth root of e? Again, we write this as a power. Fifth root is the same thing as a power of 1/5. ln and e cancel out and you get 1/5. 52. And again, all these are page 958. Okay. What is ln of e to the negative 10? Again, it's negative 10 because ln has base e. Now, they want us to solve for x. ln of x is 0.926. Okay. So since we cannot put that into the calculator because we don't know what x is, so we're gonna change it into exponential. To do so, we're gonna write this as log base e of x. We're gonna change it into exponential, so e to the 0.926 equals x. Now we put it in our calculators to get the answer, and we gotta do as many decimal places as they require us to do. So second ln will take us to e 0.926. And it's roughly 2.5244. So I do 4 decimal places usually, but depending on what they're asking for. And same thing with 68. Again, ln of x equals negative 0.001. So we change this to log base e. So e to the negative 0.001 equals x. Again, second ln key to get e right there. Second ln. So that's going to give e to the power and then negative 0.001. And that's roughly 0.999. Okay. Now 76. Let's look at 76 from page 959. Now they want us to do compare rates. An initial deposit of 30 grants, so you want to deposit 30 grants, grows at an annual rate of 8% annual rate, 8% for 30 years. For 20 years, I'm sorry, 20 years. Compare the final balance resulting from annual compounding. So they want us to do two things: annual compoundings and continuous compoundings. So for annual, we use the first formula in the handout. For continuous, PERT is only good for continuous. This is good for any other compoundings. Okay. So the principal is 30,000. The rate is 0.08. If it's annual, that means n is 1 because it's 1 times a year they compound the interest. And then 1 times how many years? 20 years. So if we do that in our calculators, 30,000 left parentheses 1 plus 0.08 over 1, right parentheses to the power 1 times 20, which is 20. And that's how much you end up with: $139,828.71 after 20 years. Now, if it's continuous, let's see, 30,000 E 0.08 times 20. Okay, so let's put that in our calculators. 30,000 E second ln to the power 0.08 times 20, and it's 148,590 and 97 cents, which is a lot more because it's continuously compounding. It's 590.97. Okay. All right. Now, excuse me. Now let's go to page 960 and look at 96. Page 960, number 96. It says, how long will it take $1,000 to double? So you have $1,000. You want to know how long it will take to double if it's invested at an annual rate of 5% compounded continuously. Okay, so continuously meaning you're using PERT. If you're starting with $1,000 to double it, you need to make it 2,000. Okay, and we want to solve an exponential equation, so we divide the 1,000. So we get 2 equals e to the 0.05t. We're stuck with exponential. We want to change it into log. So we do log base e of 0.05t of 2. So divide by 0.05. So ln of 2 over 0.05 equals t. So basically you're using the formula ln of 2 over r. You can always use this formula to double your money, as long as interest is continuously compounding. Okay, 2 for doubling and r is the rate. So ln of 2 divided by 0.05, and that's how much time you need to double your money. 13.86 years almost. Okay, and that ends 11.5.